Hey everyone, here I compile a file, a C file with the GCC, and when when I run the binary file, nothing's happened. But when I change one byte at a specific location in that binary file, and then again run the program, we have a secret string here. So it's very interesting that we can change bytes, the raw bytes, inside the binary file, and as a result we will change the behavior of the program without changing the source code itself. And how these things happen, we're gonna look at the source code. This is a small C program. It set an integer here, integer d to 0, and only prints the secret message if d is non-zero. This is an if statement. If we compile this normally, this will never print anything. We are going to change that not by editing the source code, but by editing the raw bytes of a compiled binary directly. And okay, another thing is that you need to notice here, when I compile this file, I didn't compile it with -G option without any debug symbols. Because one of my friends told me that if you're gonna do this, you need the debug symbol, but it's not about that. You don't need it. I'm compiling with plain GCC with no -G flag. That's the whole point. And -no-pi it makes the binary file so the addresses inside the binary file are fixed instead of randomized by ASLR. Each run makes this easier to follow. So whenever we run the program, all the addresses stay same. So it makes it easy to do this workflow for the reader. Every test file, every binary file, it has an address. All the bytes inside this test file has an address, just like memory. So, and we call it offset. So first thing that we're going to do, as we saw here, the def variable is defined and initialized inside the main function. So it's going to be inside the stack, and it's going to be inside the instructions of this main function. And so we use the object dump this command to decode the instruction and to see all the function inside this test binary file. So here we can see all the function of all the section and segments of the binary file. This command actually disassembles every instruction in the binary file. So here we are going to see where is the main function. The main function is here. On the left here we are seeing the addresses, the offset of each binary code, each code. For example, this byte is at this address, and this byte will be at 37. 40, 11, 37 is this byte inside the, not actually inside the file, but because this 40, the address that will be shown by obj dump is the address after running the program, so it actually gets loaded inside the memory. It's a virtual address. This column is a virtual address where this byte will sit in memory once the program is run. The next comment here is the binary code, easy. And the next one, these columns, they are translate of this binary code into the human readable form. So we can see that this sequence of binary means an Intel instruction, because we decoded with Intel instruction. It means that these are meaning that move something somewhere. It's like this. So here inside the main function we need to find that initialization of d variable, so which is exactly here. We have some move, some sub, another move which put this value 1 inside this location in a stack. But this is 1. Why? Because the last thing that I did on the test file was changing the bytes, you know. So I'm gonna compile it again, and then we will look at the file again. So yeah, here it's 0. So this is actually initialization of D. And after that, this is the obj dump also showed this, because P was a general, it was a global variable, so we can also see this, because inside the file this is another thing. After D we have P. P is a global variable, so after instruction of initialization of D we have initialization of P. So here we can see that after D we have P. So this line is 100% is initialization of D. Okay. So we need to somehow change this, change some bytes here to make 0 to 1. And here, how we can do that? We cannot go to this address and change it, because this is the virtual address. This is the final address that we will, the program will sit, this instruction will sit inside the memory after the program, the program is loaded inside the memory. We somehow need to translate this address into an offset inside the file itself. So this line only exists inside the memory address. It only exists once the OS loads this program and runs. But right now, I'm not running anything. I'm editing the file sitting on the disk. We are going to change this file, the binary file. So, because all of these instructions, actually they are sitting inside the binary file. So, and when OS loads it, it just takes this binary file and load it inside the memory and give it a new address, which is this one. We know that they have a byte offset counted from the start of the file to offset, from the start of the file until the end of the file. So the offset of the first byte inside the file is 0. Now we just need to see how we need to see how the OS loader takes these bytes and does this translation. For that, every binary file, the ELF file, has a header. So we looked into the header with read elf -l test. Initial load segments. Instruction tell these loads are the instructions telling the OS loader, for example, for this load, takes the bytes starting at this file offset, you know, here, at this file offset, and load it and place it in this memory address. Okay, so every byte starting at this address will be loaded into this memory address. So if we move this, we go to the 0, 1, it will go to this address 1, and so on for this load. So this first load we handle the byte from inside the binary file. It will handle the byte starting from 0 until this one, until this offset, 1 byte before this offset, because this offset is going to be handled by another load, which is the load of a main function, which is this one. Loading these instructions inside the memory will be handled by this load segment. The main function starts at they are loaded inside this location of the memory, and this location inside the memory is in the range of this load, because it will take the offset, the binary at this location forward, and it will load them inside this location. And this one is smaller than this one. Okay, it's smaller than this one, but the third one is not the case, because it is bigger than what we want. This one is bigger than this, so this one is responsible, the second load is responsible to load the main instruction. So here we need to extract the shifts that OS loader will do to load the instruction inside the memory. So that shift can be easily extracted from these two things. So here we know that the binary at this location will go inside this. So if this location, so if we subtract this from, what was that, from this, we see that it will be easily one, two, three, four, 1, 2, 3, 4. It will be this. So this is a shift. Easily we can, for this location, we can do this minus, for example, this 1, 2, 3, 4. If we subtract these two, we will have 0x 42. So this address will be the address of these bytes inside the binary file before loading into the memory. So we can check it by the command of xxd. This is this command will do this. It will dump the raw file bytes starting at a given offset, this one, this address, and seek and fetch the 7 bytes from test binary. So these are the bytes in the raw file, and we check if they are same as what we have here. They are same. 4, 5, 6, they are same. So it get confirmed that, I'm sorry, they are same with this, actually, in another 0. So they are same. These bytes actually are for the instruction. They are OP code and all of the and addressing info, responsible for the instruction, doing all of these things. But and another thing that we know is Vim. We need to see it. Here D is a int, has a int type, so it's an int. So int on a machine has a 4 byte. So this is another way to see how many bytes inside that instruction is actually responsible for representing the value. So these 4 bytes, which all of them are 0, they are responsible for the value of D. And inside the machine, it's a little Indian, and the least significant byte will be sit at the leftmost section. So for make it 1, we need to change this byte and not this byte. So 42, 43, 44, and 45. And the address inside the file was this. So therefore the address we need to change the bytes in is this address. So print is actually, this command was actually doing that, writing the byte 1 inside the test binary at this address and overwrite it in place. Does not truncate the file to this one, but so it won't destroy the file actually. Just change that byte and leave all others bytes intact. Do this exactly. Right now it's 1. Before it was 0 and right now it's 1. So right now if we run the program, we need to see the secret. We saw the secret and we change by changing the raw byte. Or again, if we look at this, we can see that exactly. We change it again. And also for the knowledge, this is a comparison and this is the jump. This one says that if the value of d is equal to 0, so you will jump. But we change it to 1, so it's not equal to 0 and it won't jump, and etc. Thank you for watching.